Hello everyone. Today we are going to go through lab 9, which is register bank and shift register. So we have two parts. We'll go through each part and its explanation and components one by one. So these are the two parts. The first part is register bank, which is shown by the circuit here. We'll go through the explanation but I've added the circuit just so you know that which circuit we are referring to when we say register bank. And the second part here is shift register. I'm going to add a pointer. Alright, so second part here is the shift register. This is part of the shift register. It gives you a sample of the circuitry. This is not a complete shift register design. The dots indicate that you need to complete the circuit. Alright, having said that, let's get into the details. So for the first part, we are going to see the concept and the operations that we're going to perform on the register bank. What the register bank is, the circuit components and examples, and we're in detail look into the implementation steps, what are the inputs and outputs, and again at the end, as we end every time with the waveform cases and the demo cases that you need to show to complete the lab report and demo. Alright, so the concept of a shift register is that we saw that we can store data in the register, right? Now the concept of this register bank is that we have a bank of registers, which means that we have multiple registers, and we should be able to put data in the register, take data out from the register, and shift data from one register to the other. So imagine you have this register 1, so you should be able to put data in the register, take it out from the register and display it on the 7-segment display or the LEDs. But at the same time, you have multiple registers. So instead of 1, you have, let's say, 3 registers. You should be able to perform these operations on any of these registers, and you should also be able to shift data from one register to the other. It can be the source can be any register and the destination can be any register. So we need to create a circuit like that. But that was the main concept behind it. So we'll look into the circuit components now. We need a 8-bit parallel in parallel out register, and we need 3 of them because we are going to create a bank. So we have our registers here. Then we need a TSBA because when we are putting data from your switches into the registers, we want to have a control over it. So the TSBA will enable you to have a control over whether you want to let the data flow from the keypad to the registers or not. So let's say you have a TSBA, and then that will control the flow of the input from your switches to the registers, so that if the TSBA is enabled, then the data will flow. If the TSBA is disabled, then the data will not flow. Then we need a 7-segment ROM display so that we can show data from the registers on the fancy 7-segment. So that is there. Then this is the last part. We need 2:4 decoders to control the data flow. So we saw that we need to manage the flow of data, that is the input, that is putting data in the registers, taking data out from the registers, and shifting data from one register to the other. We are going to do that using 2:4 decoders, and we'll see the details of that later, but that is the additional part that we are going to build, which will intelligently control the flow of data in your register bank. Okay, so let's take a look at the register that we're going to use in this lab. It is an 8-bit parallel in parallel out register. The parallel in parallel out register that you created in last lab, which is lab 8, was using D flip-flops, but it did not have input enable and output enable, right? So we could not control whether we want to put data in only one register and close the input of the other registers, right? So we are going to use a better component, which is IC 74173 in Quartus. It can be seen here. So this one IC is actually a 4-bit register. So the 4 inputs coming in the IC are in 0, 1, 2, 3, and the rest of the 4 inputs, which are in 4, 5, 6, 7, are going to the other IC. And together we are creating an 8-bit register. So if you notice, the data pin 7.0 has 8 inputs, out of which the first 4 go into one IC and the later 4 go into the next IC. Now, the good point about this IC is that it has input enable and output enable, which is what we need to control the data flow in the register and out of the register. So if you want to allow the data to flow in the register, you enable the inputs enable, and if you want the data to flow out of the register, you enable the output enable, right? So this circuit, which is given on the challenge page, is what you will be creating using this IC 74173 to create the register required for this lab. Now remember, this is one register. You will create this and save it as a symbol and use that symbol as one register, and you need 3 of these registers. Alright, now these registers also have a clear and a clock, and all the registers will have their clear and clock commonly connected to each other. Okay, let's move on. Now we have this TSBA, which we already are familiar with. We constructed this in lab 5. We are going to use the tri-state buffers to create an array of 8 tri-state buffers, which will have a common enable, and that will allow the flow of data from input to output if the enable is on, right? Now we'll again create this circuit, save that as a symbol, and use that as our TSBA. Alright, now let's look at the ROM display that we are going to require, which is similar to what we created in lab 7, but we are going to create the ROM again. You can copy paste the binary to bcd.mif file that you created in lab 7. All you have to do is copy paste it from lab 7 folder to your lab 9 folder, and add this ROM, and make sure you specify the parameters properly the way you did in lab 7. If you remember, you also did that in lab 8, so I guess you have a good practice of doing that by now. Alright, now, okay, so this is an important part of this lab. Before we dive into how 2:4 decoders are used to control the data flow in our register bank, let's have a quick revision of what 2:4 decoder is. Okay, so 2 represents for the number of inputs, so we have 2 inputs. 4 represents the number of outputs, so we have 4 outputs. And for a given input, you have a certain action that is happening. So if your input is 0, 0, only the line 0 is activated and everything else is off. If your input is 1, which is 0, 1, line 1 is activated. If your input is 2, which is 1, 0, line 2 is activated. If your input is 3, which is 1, 1, line 3 is activated. Simple, right? Okay, so let's see how we use this. We have this decoder, and then we have 3 registers, remember? Now we need to control the input enables of these registers using this decoder. The idea is that if input enable, I'm gonna use the pointer again. So the idea is that if the input enable of R1 is on, the data will flow in R1 only, right? Now we saw that if your input is 1 here, then your line 1 is on, right? So what we can do is, we can connect line 1 to register 1's input enable. We can connect line 2 to register 2's input enable. and we can connect line 3 to register 3's input enable. What this will do is, so let's see how this will work in action. So if your input to the 2:4 decoder is 0, 1, which is 1, it will enable the input of R1, and then data will flow in register 1 only, right? If your input to, I'm going to use a pointer. If your input to decoder is 1, 0, which is 2, then the data will flow only in register 2, which is this. If your input to 2:4 decoder is 3, which is 1, 1, the data will flow only in R3, right? Now, because line 0 is not connected to anything, because we don't have a register 0, it doesn't matter what you do when you have input as 0, 0. Now, because we are controlling the input enables of registers using this decoder, we call it the input selector. So it decides where I'm putting my data in, right? Remember that. So your in0, in1 decides where you're putting your data in. Similarly, we will see how the data is controlled on the output enables. So we have the 3 registers, we have a 2:4 decoder, but now our inputs are out 0, out 1, and they are going to control the output enables of the registers. So I'm going to connect line 1 to the output enable of register 1, line 2 to output enable of register 2, and line 3 to the output enable of register 3. And now what will happen in action is that if your input to the 2:4 decoder is 0, 1, which is 1, it will only enable the output of register 1, and the data will flow out from register 1, right? So if you want to make data flow from a particular register, you have to give that number to the out 0, out 1, right? So similarly, if your input to the out 0, out 1 is 2, which is 1, 0, the data will flow out from register 2. If the input to out 1 out 0 is 3, which is 1, 1, then the data will flow out from register 3. The line 0 of output enable is connected to the TSB enable, because that is also a block that we need to control the data flow from. So if you want to put data, allow data coming from the switches, then you need to give out 0, out 1 as 0, 0. And we'll see the example very soon. And similarly, because this decoder is being used to control where is the data coming out from, we call it the output selector. Simple? Alright, now let's move on. Now, you don't have to create the 2:4 decoders. We have an IC for it. The IC 74139 in Quartus has two 2:4 decoders. So you can see that it has, this is a sample circuit given on the challenge page. Once you have this IC, then you will create this circuit. The first two inputs will be in 0, in 1, and then out 0, out 1. And then we have decoder selector 0 and decoder selector 1. So the input enable 0 over here, that has not been connected to anything because we don't have any register 0, right? The output enable 0 is used to enable TSBA, like we saw. If you are seeing here, all the outputs of the IC are bubbled, which means they are active low. But our TSBA is active high. So we add a NOT gate here so that our TSBA is on when the input to the TSBA enable is 1. So that's a normal high logic, right? And then the decoder selectors that you can see over here, the decoder selector 0 and 1, they should be grounded because they have bubbles here, which means they're active low. So you want both the decoders to be on at the same time. So you'll be grounding both of them. So you don't have to assign them to any switch on the board. Okay, so now this is how the interconnections of all these components will look like. There will be a register clock which is common to all the registers. You can see that here. The wiring is not done because otherwise it would have looked very clumsy. But imagine that this clock is common to each register. Now there is also another clock, which is the display round clock. We will assign that to pin M9 like we did in lab 8. That is an auto clock on the DE board, so you don't have to control that clock, and the display will automatically refresh itself. Then all the blocks, inputs and outputs, should be in bus form. So you can see that each register has an 8-bit bus going in and coming out of it. The keypad and the display itself as well have bus inputs and outputs. This will allow you to connect your circuit easily and avoid any nomenclature errors that you might have due to trying to convert single wires into buses and buses into single wires. So it's a good practice to have, and it will also help you have your circuit more organized. All right, now in total you have several inputs, but only the outputs that you have are just the 7-segment display outputs, which are 24 outputs, out of which let me write it down. So you have 24 outputs, which is 23.0, out of which you are not connecting bit 7, you're not connecting bit 15, and you are not connecting bit 23, because if you remember, they were the padding bits, right? So you're not connecting these to any pins, but rest of them you'll be connecting to your 7-segment display, right? So the 0 goes here, 1, 2, 3, 4, 5, and 6. And then 7 not connected, 8, 9, 10, 11, 12, 13, 14. 15 not connected, 16, 17, 18, 19, 20, 21, 22, and 23 not connected. So that is your 7-segment display output. Now let's take a look at the inputs. In inputs, we have 8 bits, which are switches. So your data will come from 8 of the switches. Then you have in 0, in 1, which will control where is the data coming in from. I mean, where are you putting the data in which of the registers? So if your in 0, in 1 is 1, the data will flow in the register 1, right? All right. Similarly, you have out 1, out 0, that determines where is the data coming out of. So if your out 1, out 0 is 3, which is 1, 1, let's say, then the data will come out of register 3, right? So these two, in 0, in 1, and out 0, out 1, so these are 4 switches in total, right? Then you have a register clock, which will be a push button, and then a register clear, which will also be a push button. The decoder selector 0 and decoder selector 1 will be ground, so they are not assigned on the board, they are assigned to the ground, which looks like a symbol like this. It's a triangle. You must be familiar with that. And this will be taken care of in the circuit, right? So you're not assigning decoder selectors on the board, you're assigning them to ground in the circuit itself. Okay, now let's take an example. So we saw that we want to be able to store data in the registers and display data from the registers and then shuffle it from one register to the other. So let's see how we can use these inputs and outputs that we have to actually perform these operations. So the first example is that we are trying to store 5. The data is 5, which is 00000101 in binary, and we're trying to store that in register 1, right? So here is my register. Right, here is my register 1. Here is my in 0, in 1, and here is my out 0, out 1. And this is my keypad. So my keypad should intake 00000101, right? Because that's the data I want to store. Then I want to store data in register 1, right? Let me get a pen. Okay, now I want to store data in register 1. So this number is really important. It is going to be stored in register 1. So this register and this keypad, so these two things need to be enabled, right? Now, if you remember, the output selector has its 0th line connected to the keypad, right? So my out 0 out 1 will be 0 0, and my in 1 in 0 will be 0 1, which is 1 because I want to enable my register 1. Simple. So in this example, we're trying to store 15 in register 3, right? Now the data that we're trying to store is 15, which is 0 0 0 0 1 1 1 1 in binary. So our keypad will have that. And then we need to enable register 3, right? So let me get a pointer. Okay, we need to enable register 3, and we need to enable the output of keypad. So the output of keypad is enabled by out 1 out 0 as 0 0, and the input of register 3 is enabled by in 1 in 0 as 3, which is 1 1. So once you assign these values and push the clock, the data will flow out from the keypad and will go in the register, right? Okay, now if you want to store 5 in register 3, all you have to do is change the data input in keypad, and that will be with the same input combination of in 1 in 0 and out 1 out 0. We'll be able to store the data in register 3. So it doesn't matter what data you're trying to store. The idea is that in 1 in 0 and out 1 out 0 are being used to just decide where is my data coming out from and where is my data going in, right? Okay, now let's take the last example over here. Actually, this is last but one. So let's try to display data from register 3 now. So we are not putting anything in the registers, so we can just remove any inputs from the keypad, and then we are not putting data in any register, so your in 1 in 0 is 0, right? But we are taking data out. We are taking data out from register 3, so my out 1 out 0 should be 3, and that way it will flow from register 3 to the display, and it will be displayed whatever was stored in register 3. Now in the last slide we saw the example that we stored 15, so on our display we should be able to see 0 1 5, right? Okay, now the last example, very important. Suppose you want to shift the data from register 2 to register 3 now, sorry, register 1. So you want to shift data from register 2 to register 1. Now imagine that your data is going in to register 1, right? So your in 1 in 0 should be 1, and the data is coming out from register 2, so your out 1 out 0 should be 2, which is 1 0. That is all you need to decide. What is the data coming out of and where is the data going in? Once you decide that, assign these values, and when you assign these values, the input of register 1 and output of register 2 are enabled. When you push the clock, the data flow will happen. So data will come out of register 2 and it will go in register 1, right? Okay, now as I say always, it is very tempting to implement the entire circuit and expect it to work, but it's a very bad practice. It's a good idea to implement the circuit in parts. So create the resistor symbol first, create the decoder circuit, test each components, and attach your components one by one. So you don't have to attach all the 3 resistors to your display and keypad and the decoder. Attach only one resistor and try to see if your input and output is working. Now also you can test your inputs and outputs on just the normal LEDs on your board. You don't have to test it on the 7-segment display. If your circuit is working on the LEDs, then go ahead and attach your 7-segment display and test the circuit on that. So that way, if something is not working, you know which component exactly that is, because you've performed your testing in parts. Okay, now to show waveform cases, load 1 in register 1 and then show the data in register 1. Then load 2 in register 2, show the data in register 2. So it should show 2, right? Load 3 in register 3 and show it. So now it should show 3 in the display. And now for the last example, shift data in register 1 to register 3 and then show register 3. Now that should show 1 because you shifted the data from register 1 to 3, right? So that should be shown in your waveforms. Now remember that, let me draw that here. So in this one waveform time frame, let's say this is 10 nanoseconds, this window. In this window, you will be performing one operation. So if this is your one operation, loading data, that will happen in this 110 nanosecond time frame. The second one, show data from R1, that will happen over here in the second time frame, right? So make sure that you assign the values of inputs properly. Also, you'll have two clocks, the register clock and the RAM clock, right? Make sure that your register clock is slower than your RAM clock. In other words, imagine that your register clock is varying like this. Let's say it varies after every, let's say 2 nanoseconds, okay? Now your RAM clock should be much faster because it needs to refresh the display instantly, right? So you can make this as small as 0.01 nanoseconds. That will just make sure that there is no delay between your action and display, okay? In the waveform, you have to manually assign these clock values by right clicking and then go to values and assign when the values are changing. But when you try the demo on the board, the ROM clock is assigned to pin M9, which is an automatic clock on the board, so you don't have to assign that. All you have to do is take care of the register clock at the push button, okay? Alright, now for the demo, you perform the same cases, but as I said, you don't have to take care of the ROM clock in the demo on the board because it has already been taken care of by pin M9, which is an automatic clock. Every operation that you perform, if the register clock will be required to refresh the output, okay? All right, now that was part 1. Let's go into part 2 now. In part 2, we are going to learn how to create a shift register. So for the components, we'll see how is D flip-flop used as 1-bit memory, what are 4:1 multiplexers, the bit slice of this shift register circuit, and what are the operations that we are going to perform, the complete circuit and the implementation. And at the end, like always, we'll see the waveform cases and demo cases. Alright, now let's look at the concept first. The overall concept of a shift register is that, let's say you have 3 D flip-flops, right? Now each D flip-flop is going to store 1-bit data, and suppose you stored 1 0 0, right? And then your Q2, Q1, Q0 are 1 0 and 0, right? Now you should be able to, well, first of all, load this data in these D flip-flops. The other operations are shift this data left and right. So suppose you are shifting this data towards right. Then in the next clock cycle, you should be able to, this is, let's say, first clock cycle. In the second clock cycle, you should see 0 because there is nothing on the left hand side. And then this 1 should appear here. So 1 and 0. In the next clock cycle, it should shift even further. So you will get a 0, 0, and this 1 will appear here, right? So you see this is a shift right operation. Similarly, you should be able to shift left and perform no change. No change means whatever is the output, if I press the clock, it should stay as it is. Now, these are the 4 operations that we want to be able to perform on a normal register, but we need an additional circuitry for that. So the circuitry that we need to control the data shifts is what we are going to understand today. Okay, now let's revise the concept of D flip-flop as a 1-bit memory. We saw this in lab 8, but I'm just going to quickly revise it. A D flip-flop can store 1-bit data. You have an input pin D and output pin Q. There's a preset which if you it sets data to 1. So if you press the preset, whatever is the data inside will get overridden by 1. Similarly, you have a clear. So if you press the clear, whatever is the data inside will get cleared and everything will be 0. And then you have a clock. So to make the data appear from inside the D flip-flop to the output, you need the clock pulse, right? So that is a normal D flip-flop which can store 1 bit. Now we are going to study what are 4:1 multiplexers. So a 4:1 multiplexer has 4 inputs and 1 output, as it says in its name. However, it also has 2 select lines, S1 and S0. Now the number of select lines depends on how many inputs you have, because okay, let's see why. So it's a number of 2 raised to n. This is the number of inputs, right? So now you have 4 inputs. Now 2 raised to 2 is 4. That's why you have 2 select lines. Simple. Okay. Now in Quartus, you'll have to type mux41 to get this symbol, in which the D0, D1, D2, D3 are your inputs, S1 and S0 are your select lines, and this Q is the output. Now there is an additional input which is called INH, and that's the enable of the multiplexer, right? Now what does the multiplexer do actually? So let's take a look at it. Suppose you have these 4 combinations. So these are the 4 combinations possible for S1 and S0. And suppose you have S1 and 0 as 0, then what happens is your 0th line gets connected to the output, right? If your S1 S0 is 1, which is 0, 1, then your first line gets connected to the output, and whatever is here appears at the output. So basically what you're doing is you are selecting out of 4 options, and any of these 4 options can appear at the output depending on the value of the select lines, right? Now let's see how these operations are being performed. So suppose you want to perform the load operation at 0, 0, right? So if you press 0, 0 at the select lines, you should be able to upload the data into the D flip-flop, right? So what you're doing is you're connecting an input pin to the line input 0, and as soon as you give 0, 0 as the data as at the select lines, your input 0 gets connected to the output, and then the data flows from input 0 to the D flip-flop. And that is how you load data in your shift register, by giving 0, 0 on your select lines, because your input pin is assigned to the 0th line, right? So just to summarize, if you want to perform the load operation at 0, you need to connect the input pin at the 0th line, because if you give 0 to the select lines, your 0th input will be connected to the output. Okay, now let's take the next operation. Now suppose you want to shift left when your select lines are 1, 0, 0, 1, right? So shifting left is what? Whatever is the data over in Q0, you want that to appear on Q1, right? Now the select lines control which input gets connected to the output. So if my select line value is 1, my one input will get connected to the output. So if I connect if I assign 0, 1 to my select lines, my Q0 should appear on Q1. That's why I'm going to connect the Q0 to my input line 1. So what will happen is, if I give 0, 1 to my select lines, the data will flow from in1 to the output of multiplexer and into the D flip-flop, and in the next clock, my Q, whatever was on Q0 will appear at Q1, and that is actually a shift left operation, right? If there is no flip-flop on your right hand side, so suppose this is Q0, right? There is no Q minus 1, right, in a circuit. So there is nothing to connect to the I1 of this multiplexer. So you just ground it, okay? Alright. Now similarly, let's see a shift right operation. You want to perform shift right at 1, 0. So if you give 1, 0 to the select lines, your Q1 should appear at Q0. So what you do is you connect your Q1 to I2, which is 1, 0, right? I2 of this multiplexer. Again, if there is no flip-flop, you ground it. So if this D flip-flop and multiplexer are the leftmost, then there will be nothing on my left hand side to shift towards right. So in this I2, I will be just grounding. Okay. Alright, the last operation, which is no change, is very simple. All you want to do is make sure that the output of this flip-flop stays the same even after the clock when I give 1, 1 over here. So I take that output, connect it to input 3, so that whenever I give 1, 1 over here in the select lines, my same flip-flop output goes back into the D flip-flop, and it's refreshing at every clock, but the value is staying the same because I'm feeding my flip-flop with the same data, right? So because I'm feeding it with the same data, it looks like it's staying the same, but you're actually refreshing it. Okay, now the entire circuitry kind of looks like this, but this is, you have to remember this. Okay, let me pen. So this combination of D flip-flop and the multiplexer, this is a bit slice. Now this takes care of 1 bit. You're going to create an 8-bit shift register. So you are going to need 8 of these, right? And you're going to create all these connections in that circuitry. Now remember that the select lines are common, the clock is common, and the clear is common to each register. So your S1 is going to stay the same for each multiplexer, and your S2 is going to stay the same for each multiplexer, right? So these are the common connections you need to keep in mind of. Also, it is very easy to get confused between the register that we used in this lab, in this part, the shift register, and the register that we created in register bank. These are two separate registers. The register in shift register is being created using D flip-flops, whereas the register in register bank is being created using the IC. Okay, so we are not going to create the register in register bank using D flip-flops. Alright, now let's check out the inputs and outputs. So for implementing it, we have 8-bit data. So we'll be taking that data as an input from switches, and then the select lines, which are S1 and 0, will also come from switches. The clock and the clear will come from push buttons, so key 0 and key 1, let's say, and the outputs will be the 8 outputs of the D flip-flop will go to the 8 LEDs, right? Now on the waveform, you'll be showing these operations. So you'll be loading, so let's say this is your 10 nanosecond window, 10 nanoseconds. In one 10 nanosecond window, you'll be performing one operation. So let's say you're performing load over here. So you'll give your the clock should have only one pulse. right? And then you'll assign your inputs, and you'll assign your select line values, and you'll perform the load operation in one window. In the next 10 nanosecond window, you'll perform shift left. So to perform shift left, you'll give select lines S1 and 0 as 0 and 1, right? So for load, they are going to be 0, 0. For shift left, they're going to be 0 and 1. So you need to perform shift left for multiple times so that we can see that all of your bit slices are working properly. So you perform it, let's say 4 or 5 times, and then you perform shift left, and then you perform no change. Okay. For demo, make sure that you're shifting it left at least 7 times so that we can see that each D flip-flop and multiplexer is connected properly. You do the same for the shift right, and then no change. Alright, so that was lab 9 with 2 parts, register bank and shift register. If you have any questions, please email your TAs or the learning assistants, and feel free to contact us during our online office hours and lab sessions. Do check out the web page and let us know if you have any questions. The office hours and lab session timings are listed on Canvas. Thank you so much. Have a good day.